6 years ago, we launched the African Rainfall Project in collaboration with the World Community Grid. Unlike most of their projects, which focus on medical research, we wanted to model rainfall patterns across sub-Saharan Africa on a detailed scale. Rainfall is incredibly important for the people of Africa. Most regions experience 1 or 2 rainy seasons with long dry periods in between. Over 95% of African farmers depend on rain-fed agriculture, meaning food security relies heavily on consistent rainfall. When the rains fail or there is a prolonged drought, as is currently happening in southern Africa, food production stops. Unfortunately, weather forecasts in Africa are not very accurate. A rainfall prediction for tomorrow is about as reliable as a 10-day forecast in Europe or North America. We need to improve these forecasts. This would be a great help to farmers, allowing them to time activities like sowing and spraying. People in cities would also benefit, as better forecasts would allow us to predict flash floods and issue early warnings, which would save lives. More than 80% of rainfall in Africa is produced by convective storms. These are intense rainstorms caused by the heating of the Earth's surface, which draws in moist air. These storms are often short but extremely heavy, with rainfall rates of 50 to 100 millimeters per hour. Their intensity and location can vary greatly. I remember during my PhD in Rwanda, I would stand on the hill where my house was and watch it rain heavily on a nearby hill while my house remained completely dry. To simulate these storms, we need a very fine spatial scale, ideally 1 kilometer. Even the largest computers cannot handle the entire continent at that resolution. That is where the World Community Grid volunteers play a key role. We divided the continent into small domains of 50 by 50 kilometers. Each volunteer processes one of these domains for 2 days and they send the results back. However, you cannot calculate weather in isolation. Each domain is affected by the conditions of the neighboring regions, like which way the winds are blowing. We use a global model to provide these boundary conditions at a resolution of 50 kilometers. First, we simulate a larger domain of 500 by 500 kilometers at a resolution of 9 kilometers. Then we refine the area further to 200 by 200 kilometers with a 3 kilometer resolution. And finally, we calculate the smallest domain of 50 kilometers at a 1 kilometer resolution. Each time we increase the resolution, the computing time multiplies 81 times. That is why we rely so much on the power of the World Community Grid's volunteer network. At this point, we have accumulated 0.4 petabytes of data. To give you an idea of how much it is, Lloyd Trenish from IBM, who helped enormously with setting up the project, calculated that if we stored it all on floppy disk, the stack would reach to the moon. We originally stored the data on the Dutch National Computational Infrastructure, but now it is hosted by Amazon Web Services as part of their corporate social responsibility program. The project did experience a break during the migration of the World Community Grid to the Cranwell Research Institute in Toronto. However, we are now back on track and we are close to completing 80% of the project. We expect to finish by early 2025. It has been a long journey, but thanks to the thousands of volunteers, we are nearing the final stages of the project, and the discoveries we are about to make could change how we understand rainfall in Africa.
The next step is to make all this data accessible to everyone who might want to study it. And that is where I come in. I am developing a simple user interface that will allow people to select a specific area and time period to view the data. At this stage, we cannot display the results visually, but users will be able to download the data as a netcdf file. And this is a common file format used for climate and weather data. We will also provide a basic Python script so that users can generate rainfall maps from the data. Although it is not yet as user-friendly as we would like, we are working hard to make this data available to a wide audience. In addition to making the data available, we are planning to run larger simulations at a 1 kilometer resolution. We will not be simulating the entire continent at this scale, but instead focus on smaller areas of 500 by 500 or 1000 by 1000 kilometers. And we want to see how cutting up larger regions into smaller areas affect the results. Interestingly, we have already started seeing squall lines in the World Community Grid data. Squall lines are long formations of convective storms that move from east to west. And this is a common rainfall process which we see in West Africa, for example. And these formations are much larger than the 50 by 50 kilometer domains we used for the simulations. So we are optimistic that we will be able to capture larger weather patterns by stitching together these smaller domains. The scientific discoveries that come from this project are just beginning, and we are really excited to see how this data can be used to improve weather predictions and help people across Africa.